Let's have a look at trigonometric substitution, specifically when we try to evaluate integrals. And when dealing with trigonometric substitution, there are three basic rules to follow, which can be a constant squared plus x squared, another constant minus x squared, and x squared minus the constant. And when we deal with these three rules, then you should take note for your first equation that when your two terms are added, your x will represent the constant multiplied by tan containing theta. Proceeding to our second equation, we can note that our x variable is a negative, and this means that for this equation, our x represents a constant multiplied by sine containing theta. And for our last equation, where we are subtracting with our constant, we can let our x be equal to a constant multiplied by sec containing theta. Let's try a practical example to understand what we mean by all this. Let's say we have a fraction, and in our denominator we have 4 plus x squared, and we want to find the integral with respect to x. We can then see that our denominator looks very similar to our first equation. So we can define a as 2 and x as 2 multiplied by tan containing theta. We can then find the derivative of x, which is dx, where we have 2 multiplied by sec squared containing theta. Now that we have dx and x, we can substitute it into our equation. Let's try to factor out the 4, and we are left with 2 multiplied by sec squared containing theta over 4 multiplied in brackets 1 plus tan squared theta. And from trigonometric identities, we should know that 1 plus tan squared theta is equal to sec squared. So we are then left to find the integral of theta, which will remain a whole theta plus a constant. And to finalize our answer, we need to find theta in terms of x. So we can make theta the subject of the formula for the part where we defined x. So theta now becomes the inverse of tan, where we have x divided by 2. Now we can substitute theta into our equation, and so the final answer for this example is a half multiplied by the inverse of tan containing x over 2 plus the constant. Let's try a new example where we want to find the antiderivative of x squared over the root of 9 minus x squared with respect to x. And for this example, we can see that in the denominator where we have 9 minus x squared, it resembles our second equation where we have a squared minus x squared. We can then see that our a is equal to 3, and then we can let our x be 3 multiplied by sine containing theta. And then we can see that the derivative of x with respect to theta would be 3 multiplied by cos containing theta multiplied by d theta. We can now substitute our parameters into our equation. So our equation now becomes the integral of 9 multiplied by sine squared containing theta multiplied by 3 with cos containing theta, and we integrate with respect to theta over the root of 9 minus 9 sine squared containing theta. We can then simplify our equation by factoring out the 9 and also taking out the constant. So we are then left with 27 over the root of 9 multiplied by the integral of sine squared containing theta multiplied by cos containing theta with the integral with respect to theta over the root of 1 minus sine squared containing theta. Let's simplify our new equation, where we can see 27 divided by the root of 9 will be 9, and we take the integral of sine squared containing theta multiplied with cos containing theta, where we take the integral with respect to theta over the root of 1 minus sine squared theta. But from trigonometric identities, we know that cos squared theta is equal to 1 minus sine squared theta. So we can write the root of cos squared containing theta. We are then left to find the integral of sine squared containing theta with respect to theta. We can now solve our equation, where we should recognize the trigonometric identity of cos 2 theta is equal to 1 minus 2 sine squared theta, where we can make sine squared theta the subject of the formula. So we are left with 9 over 2, where we have the integral of 1 minus cos 2 theta with respect to theta. And when we evaluate this equation, we are left with 9 over 2 multiplied by theta minus a half sine containing 2 theta plus a constant. We can now find theta by making it the subject of the formula where we defined x, meaning that theta is equal to the inverse of sine containing x over 3. And when we substitute theta into our equation, then we are left with 9 over 2 multiplied by the inverse of sine containing x over 3 minus the half of sine containing 2 multiplied by the inverse of sine containing x over 3 plus a constant. And that would finalize our answer for our second example.